In this R code tutorial, we'll explore how to build and apply the k-nearest neighbors algorithm using our tidy models tools. Specifically, we'll use KNN to model college and university graduation rates by 3 predictors: per student instructional expenditures, typical enrollment in the first year class, and whether or not the institution is private. To begin, we'll load the packages we'll need. This includes the usual tidy models and tidyverse, as well as a new package we haven't used yet, KNN. And yes, there are 2 Ks and 2 Ns here. We'll also need the ISLR package, which has our college data that we'll use in the analysis. And once we load that data, we'll also wrangle it a little bit. And take special note here that when I wrangle that, I'm just selecting the 4 columns that correspond to the 4 variables in our analysis. Okay, so in part 1 of the tutorial, we'll build the KNN for a range of K tuning parameters, where K is the number of neighbors that we'll use in our predictions of graduation rate. The process will be this. We're going to define and use the same workflow to build and compare multiple KNN models, where each model is going to use a different value for tuning parameter K. Mainly, we don't know what an appropriate number of neighbors K is yet. So we'll try a bunch of these values. And again, we don't want to reinvent our process each time, which is why we're going to rely on a workflow that we'll define and use each time through. In step 1 of this process, we need to specify the KNN algorithm. Now, up to this point of the semester, we've always started with linear reg, because every algorithm or model building algorithm we've used so far is a type of linear regression. But now we have a different type of algorithm, which is non-parametric. It is not doing linear regression. For KNN, we are going to be using the nearest neighbor model. We're still in the regression setting or mode, so I'll set the mode to regression. Mainly our outcome variable graduation rate is still quantitative. Now that we're doing a new type of algorithm, we'll also need a new engine or function for this task. And this will be KNN. That comes from the package that we loaded earlier. Now, since the KNN algorithm depends upon the tuning parameter K, we have to set the arguments for our KNN function. The argument that's relevant here is the number of neighbors that we'll use in our analysis. And we don't know what this is yet, so I'm not going to plug in a specific value. I'm just going to say, I need to tune that still. So I'll run that chunk, and notice it just, again, tells me what I told it. What type of model am I going to build? But of course, I haven't actually built a KNN yet because I haven't even given it any data or variables of interest. And that's the next step. So in step 2, we'll create our variable recipe. We start with the recipe function, and we specify the variables of interest in our analysis. Now, I've already forgotten how graduation rate is recorded in the college data set, so let me look that up and make sure I'm getting the right thing. So let's see, names, college, grad rate, capital R. Okay, so I want to model grad rate by every possible predictor in this small data set. And so these are my ingredients, and these ingredients are located in the college data set. Now for KNN, we need to do some pre-processing steps. We'll start with step NZV. That's going to remove all predictors, or basically any predictor with near zero variance, NZV. I also, for all nominal predictors, that is, all categorical predictors in the dataset, I want to turn these into dummy variables so that I can basically turn the categories into 0, 1 information that can then be used by our mathematical algorithm. For all numerical or quantitative predictors, mainly including expenditure and enrollment, I want to normalize those predictors. So I want to get rid of any predictors with near zero variance. For all nominal or categorical predictors, I want to create dummy variables. And then for all numeric predictors, or quantitative predictors, I'm going to normalize them. And before, when I said all numeric predictors, I mentioned expenditure and enrollment, but this is also going to normalize the dummy variables that I created in the previous step. So we've defined our variable recipe, and this confirms what our recipe is. Okay, and so in step 3, I want to combine the model and recipe into our workflow specification, and I'll store this as workflow, or KNN workflow. To create this workflow, I start with the workflow function, and then I want to add my recipe, which I stored simply as variable recipe. And then I want to add the model that we're going to use to build our KNN algorithm, and that was stored in KNN spec. So basically in this step, I'm specifying what algorithm do I want to use and to what relationships or variables am I going to apply that algorithm. Okay, so now we have our workflow. And so we're in our final step 4 of building our models. In this step, we want to use our KNN workflow each time to build 50 different KNN models using a range of K tuning parameters from 1 to 200. And then I'm going to evaluate each of those using tenfold cross-validation. All right, so we'll start with the seed, mainly since we're going to be calculating cross-validated MAEs. We need to set the seed to reproduce that process since there's randomness involved. I'm going to give a name for my object that it's going to store all 50 of my models. And then to go through this process of building these 50 models, I start by specifying what is the workflow that I'm going to use each time through. And then recall that we apply this workflow to the function tuneGrid. Mainly, I'm going to tune the algorithm specified by this workflow for a grid of possible tuning parameters. And in the first argument to tuneGrid is where I specify what my tuning parameters are and what values I want to try. So here, the name of our tuning parameter is called neighbor or neighbors, and I want to try a range from 1 up to 200. I keep saying 100, a range from 1 to 200 neighbors, and I want to try 50 values in that range. And then once I build my KNN models for each value of K in this range, I want to, again, evaluate the model using tenfold cross-validated MAE. So here to vfold CV, I specify what's the data that I'm going to use to define my random folds and how many folds do I want. We're doing 10 folds. And for each of those cross-validated metrics, we're going to record the cross-validated MAE in or using metric set. And so I don't know why this is taking a minute to run. There we go. It shouldn't take that long, but it did. So now we have KNN models. And again, that stores 50 different models. I can check it out. It's not going to give me much information because in the background of KNN models, I have information about all 50 KNNs and their cross-validated metrics and the information that they need to run in order to make predictions. So what we're going to do next is tune the KNN model, basically narrow it down to a single final KNN model. So again, we've built 50 KNN models for 50 different values of K, and so we want to compare them with respect to their CVMAE in order to pick which K to use. So I can start by calculating the CVMAE for each KNN model. All of that information is stored in my mega object, KNN models, and then we'll use our usual collect metrics function to pull out the information about the CVMAE for each of our 50 models. So for example, in the first row, notice for my KNN model that used one neighbor, the typical prediction error was around 15.88. Again, this is the typical prediction error when using the KNN with k equals 1 neighbor to predict graduation rates. So it's off by almost 16 percentage points. And we could peruse this table, but again, it's easier to visualize this information. And so what we'll do next is for each of the 50 KNN models, we'll plot the CVMAE on the y-axis versus the K tuning parameter that we use for the model on the x-axis. So again, all of this information comes from our mega KNN models object, and our function is just what it was for lasso when we were tuning our lasso. Specifically, the function is autoplot. So when we look at this plot, or the auto plot, again, the y-axis is the MAE or cross-validated MAE in particular, for each of our models. And on the x-axis is the number of nearest neighbors, or the K tuning parameter for the corresponding model. So each dot here represents a single of our 50 models. So we have 50 dots, 50 models. Now for K nearest neighbors, I can essentially just pick the K that minimizes the CVMAE. I don't have to worry about parsimony as much because, well, we don't have predictors, for example, that we have to kick out here. All we're doing is deciding on neighbors to use in our analysis. So the smallest cross-validated MAE is best. It looks like the model that gives us the smallest prediction errors has a number of neighbors K around 25-ish. But it's tough to tell, at least for me. And so we'll use R to pull that information for us. Specifically, we'll use R to pick the value of K which produced the KNN with the lowest or best CVMAE. And I'll store this as best K. So again, this is all stored in the background of KNN models. And we'll use our function, again, that we used in lasso to select best. Whoops. So best K, select best. That is, select the best KNN model according to the CVMAE. And when we check out what's stored in best K, it tells us that the number of neighbors that gives us the best or lowest prediction errors was 33. So I was off a little bit. So let's go back up to our plot and notice where 33 falls on this plot. Well, 33 is somewhere around here, pretty close to where we thought, I guess. Not too bad. Now notice when we look at the plot here, we can again approximate that for K equals 33 neighbors, the typical prediction error is going to be, I don't know, a little bit above 11. And we want to get a more precise metric. And notice that we can't get that precise metric by best K. So best K, all it's storing is the number of neighbors, but not the corresponding error for the model that uses this number of neighbors. So to get that information, or specifically to get the CVMAE for this particular model, I can start by my big object of all 50 KNN models, collect metrics, and recall that this gave me the CVMAE in the mean column for each possible value of my K parameter. And I just want to pick neighbors equals 33. So I'm going to filter this to say, show me the row that corresponds to 33, because that was my best value for K, the number of neighbors. So in this case, we've confirmed that if I use a neighborhood of 33, then I would expect the corresponding prediction errors of graduation rate to be off by roughly 11.3 percentage points. Okay. So it remains to finalize the best KNN model. So we've identified the best K that gives us the smallest prediction errors, and we want to use that to build just one final model of grad rate that we'll use for future predictions. So here in our final KNN, To build our final model, we start with our workflow. This is the same workflow that we used to build all 50 models, so we'll use it again to build our final model. And to finalize the workflow, now that we know what tuning parameter we want to use, we'll use the function finalize workflow. And the parameters here that we want to use to finalize our workflow is our k value of 33, which is stored in best k, along with some other information. And so now that we have our general KNN workflow and how to finalize that for our selected value of k, we can now fit this final model to the college data. And so now we have our final KNN model that uses that best k. Now, you might feel tempted to do what we've done with every other algorithm thus far, mainly the lasso and least squares, and check out a tidy table. But notice that when we do, we get an error, which is why I've said don't evaluate this if I were going to knit the document. The reason is that typically when we get a tidy table for our least squares or lasso results, right, it's a table of coefficients. But again, the KNN model doesn't give us any coefficients. We basically can only use it to generate predictions. So there is no tidy summary here, but we can use the final KNN for prediction, which we'll do next in our final step. So suppose that we want to predict graduation rates at a private school with per student instructional expenditures of $10,000 and a typical first-year enrollment of 500 students. Now suppose that this school doesn't exist in our data set, which is why we want to make a prediction. In that case, we can just define a new data frame, which we'll store as new school. And in this data frame, we need to specify the values of our predictors. So recall that in general, when we look at the head of our college data set, it gives us a sense of how our predictors are stored, named, and recorded. Okay, so in our data frame, we wanted to say that we have a private institution. So notice private starts with a capital P, and since it's a private school that we're trying to make a prediction for, we'll say capital Y, yes, in quotes. And in our fictitious school, the per student instructional expenditures are $10,000. And so I'll record that as capital E expend equals 10,000. And for this school, our capital E first year enrollments were 500. So all I'm doing is setting up the school for which I want to make a prediction. And this is stored in a data frame. Simple data frame with one row. So now what I can do is take my final KNN model and I'll use it to predict the graduation rate for this new school. And the predicted graduation rate is roughly 75%.